Now we'll see problem 4. Test for convergence of the series summation n equal to 0 to infinity minus 1 whole power n into n plus 1 into x power n with x less than half. Given series is summation n equal to 0 to infinity minus 1 whole power n into n plus 1 into x power n. Right? It is of the form, even though it is not mentioned that absolutely or the conditionally convergent, we can make use of the same concept over here. Apply mod and turn it to a positive series, and then you can make use of the suitable positive series test. See that it is involving x power n's, so you can either make use of Cauchy's nth root test, or you can also make use of D-Allenby's ratio test. I told you already that we use for many cases D-Allenby's ratio test. Okay, except few like logs. So it is of the form summation n is equal to 0 to infinity un, where un is equal to minus 1 whole to the power of n into n plus 1 into x power n. Then mod un is equal to n plus 1 into mod x power n. Right? If you apply mod, this will become 1. Now I'll apply D-Allenby's ratio test. Limit n tends to infinity. Mod un by un plus 1 is equal to limit n tends to infinity n plus 1 into mod x power n by n plus 2 mod x power n plus 1. So this is equal to limit n tends to infinity, n common if I take, I'll get 1 plus 1 by n by n 1 plus 2 by n. And here this and this, after cancellation, I'll get the answer as 1 by mod x. Then after this cancellation, I'll get the answer as 1 by mod x, because this will give the answer as 1 plus 0 and this will give the answer as 1 plus 0. So I'll get the answer as 1 by mod x. And this is like L. In D-Allenby's ratio test, when L is greater than 1, it converges. When L is less than 1, it diverges. Right? When L equal to 1, test fails. So here, summation un converges for 1 by mod x greater than 1 or mod x less than 1. Since x is less than half lies in mod x less than 1, so therefore summation un converges for x less than half. Here mod x less than 1 means minus 1 less than x less than 1. So plus half falls in that, right? So therefore because of that condition we can say that this series converges for x less than. Test whether problem 5 show that the exponential series 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial plus and so on is absolutely convergent. Given series is 1 plus x square by 2 factorial plus x cube by 3 factorial plus and so on. It is of the form summation un, where un is equal to, see the terms what we have here, 1 plus x square by 2 factorial, x cube by 3 factorial plus and so on. Okay, so I'll write here n equal to 0. Okay, then un will be equal to x power n by n factorial. Un is equal to x power n by n factorial. See that here we are not given whether x is positive or negative. So I cannot say that it is greater than 0. Un is equal to x power n by n factorial. I cannot say that it is greater than 0 because x value is not given there. So if I apply mod, then I can say that it is greater than 0. Mod un is equal to mod x power n by n factorial is greater than 0. Now for this again solving, because it is involving x power n and n factorial, again I'll make use of D-Allenby's ratio test. Now limit n tends to infinity, mod un by un plus 1 is equal to mod x whole power n by n factorial. Okay, limit n tends to infinity by mod x whole power n plus 1 by n plus 1 factorial. Now rearranging this, I can write it as limit n tends to infinity mod x whole power n by n factorial into mod x whole power n into mod x whole power 1 by n plus 1 factorial. I can write it as n plus 1 into n factorial. Then okay, this I should write it as okay divided by, then I'll write that clearly here. It is equal to limit n tends to infinity mod x whole power n by n factorial into, when I take divided by it gets reversed, so I'll get that as n plus 1 into n factorial divided by mod x whole power n into mod x, right? So here the terms mod x whole power n, mod x whole power n and n factorial will get cancelled. Then this is equal to limit n tends to infinity, okay, n plus 1 by mod x. As n is tending towards infinity, its answer will be equal to infinity provided mod x is not equal to 0. Mod x should not be 0. Otherwise it becomes 0 by 0 form or infinity by infinity form or infinity into infinity form. Indeterminate. So to avoid that, write here that mod x is not equal to 0. So this limit n tends to infinity, n plus 1 by mod x is equal to infinity. See that this infinity means greater than 1. Okay, in D-Aripmet's ratio test we have learned that when the limit is greater than 1, the given series converges. Okay, it implies summation un with mod converges. Okay, converges for mod x not equal to 0. It implies summation un converges absolutely. Okay, for mod x not equal to 0. But what happens when x is equal to 0? We need to check. Okay, when x is equal to 0 is put in given series, we get 1 plus 0 by 1 factorial plus 0 square by 2 factorial plus and so on, which is going to give the answer as a finite value. So therefore, given series converges absolutely for all x, converges for all x. Okay, problem 6. Test for convergence of the logarithmic series x minus x square by 2 plus x cube by 3 minus x power 4 by 4 plus and so on. So given series is of the form is x minus x square by 2 plus x cube by 3 minus x power 4 by 4 plus and so on. It is of the form summation n is equal to 1 to infinity un, where un is equal to minus 1 whole to the power of n minus 1 into x power n by n, right? So apply mod to this so that it becomes a positive term, hence it gives a positive series. So x power mod x power n by n, which is greater than 0. So it gives a positive series. As it gives a positive series, so we can make use of positive series test. Okay, now limit n tends to infinity, again I am using D-Aripmet's ratio test. Mod un by un plus 1 is equal to mod x power n, limit n tends to infinity, mod x power n by mod x power n plus 1 by n plus 1. So which is equal to limit n tends to infinity mod x power n by n into, reverse it, so that becomes n plus 1 by mod x power n into mod x. So this term and this term will get cancelled, right? So we are going to get the answer as limit n tends to infinity n plus 1 by n into 1 by mod x. Okay, so this is equal to limit n tends to infinity, n common if I take, or if I solve this, I'll get that as 1 plus 1 by n into 1 by mod x, right? So this gives the answer as 1 by mod x. So summation un converges if 1 by mod x is greater than 1 or mod x is less than 1, and diverges for mod x greater than 1, and test fails for mod x is equal to 1. So what happens when mod x is equal to 1? We need to check. Okay. Case 1. Take x is equal to 1. X is equal to plus or minus 1 in given series. So what happens to the given series? We need to check. Okay. 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus and so on is convergent. We know that it is an alternating series which is convergent by Leibniz test. Take x is equal to minus 1 in given series. Then we get that as minus 1. So that becomes minus 1, minus 1 by 2, minus 1 by 3, minus 1 by 4 and so on. Right? So I can write it as minus of 1 plus 1 by 2 plus 1 by 3 plus and so on, which is divergent by P series test. Its nth term will be 1 by n. And we know that 1 by n power 1, summation 1 by n power 1 diverges by P series test. Right? Even if we apply minus sign, nothing will happen because we have learned the characteristics of the series. Nature of the series will not change even when it is multiplied with some constant. So find out its nature and multiply it with minus, nothing will happen. The nature is not going to change. Okay. So this particular series has divergence and this particular series is convergent by Leibniz test. So therefore, summation un converges for, okay, here mod x less than 1. So I can write minus 1 less than x less than 1. Right, according to this, minus 1 less than x less than 1. And see that here when x is equal to 1 also it is convergent. So therefore I can write here equal to. Now we'll see the next problem. Problem 7. Test for the convergence of the series 1 minus x square by 2 factorial plus x power 4 by 5 4 factorial minus x power 6 by 6 factorial plus and so on. Given series is 1 minus x square by 2 factorial plus x power 4 by 4 factorial minus x power 6 by 6 factorial plus and so on. Right? It is of the form summation n equal to 0 to infinity x power 2n by 2n factorial with summation n equal to 0 to infinity un, where un is equal to minus 1 whole power n into x power 2n by 2n factorial. Now apply mod to this so that it becomes or it gives a positive series. Mod un is equal to, so this will vanish, so I'll get mod x power 2n by 2n factorial. Then by applying again the D-Allenby's ratio test, we get that as limit n tends to infinity mod un by un plus 1 is equal to limit n tends to infinity mod x power 2n by 2n factorial by mod x power 2n plus 2 by 2n plus 2 factorial. Okay. For un plus 1 replace n with n plus 1. So that becomes 2n plus 2. Then I can write this as limit n tends to infinity mod x power 2n by 2n factorial, okay, into, reverse it. I can write 2n plus 2 factorial as 2n plus 2 into 2n plus 1 into 2n factorial. Okay, so I can write here 2n plus 2 into 2n plus 1 into 2n factorial divided by, I can write mod x power 2n into mod x power 2 like this. Okay, so here I can cancel this term, and I can cancel this term and this term. Limit n tends to infinity mod un by un plus 1 is equal to limit n tends to infinity 2n plus 2 into 2n plus 1 by mod x whole square. Here when I apply limit n tends to infinity, I am going to get the answer as infinity, which is greater than 1 provided mod x is not equal to 0. Then you see that here I am getting the answer as greater than, it's equal to infinity, which is greater than 1 provided that mod x value is not equal to 0. So therefore I can say that summation un converges absolutely for all x except x is equal to 0. But what happens at x is equal to 0, we need to find out. Okay, so put x is equal to 0 in given series. Then we get 1 minus 0 plus 0 minus 0 plus and so on, which is equal to 1. See that I am getting sum of the given series as a finite value 1. So therefore, okay, it also converges for x is equal to 0. So therefore, given series converges absolutely for all x. Then we'll see the next problems based on interval of convergence. How to find out the interval of convergence. Problem 8. Find the interval of convergence of the series x square by 2 plus x cube by 3 plus x power 4 by 4, okay, plus and so on up to infinity. Given series is x square by 2 plus x cube by 3 plus x power 4 by 4 plus and so on. It is of the form summation n is equal to 2 to infinity un, where un is equal to x power n by n. Suppose that it is starting from 2. Neglect 1 or 2 term, nothing will happen, right? So we wrote in the characteristics of the series, by adding or deleting finite number of terms, it doesn't affect the nature of the series. Suppose that we deleted or add starting terms, so nothing will happen to the nature of the series. Then see that here we are not given that whether x is greater than 0 or less than 0, right? So we have to apply. I cannot write that this is greater than 0. I can write that only when I apply mod to that. Now mod un is equal to mod x whole power n by n. This is greater than 0. Okay, we need to remember this, and we have to write that it is greater than 0 or not. It gives a positive series, so we can make use of the positive series test. Now limit n tends to infinity, mod un by un plus 1 is equal to limit n tends to infinity mod x power n by n divided by mod x power n plus 1 by n plus 1, which is equal to limit n tends to infinity mod x power n by n into n plus 1 by mod x power n into mod x. So this and this will get cancelled. So this is equal to limit n tends to infinity n plus 1 by n, so which gives 1 plus 1 by n into 1 by mod x. Now this is going to give the answer as limit n tends to infinity, okay, mod un by un plus 1 is equal to 1 by mod x. Okay, it converges for 1 by mod x greater than 1 or mod x less than 1. Test fails for mod x is equal to 1. See that I need only interval of convergence. I don't want the condition for divergence. Okay, so I can write here minus 1 less than x less than 1. And mod x is equal to 1 implies x is equal to plus or minus 1. Now check what happens to the given series when I put x is equal to 1 and x is equal to minus 1. So case 1, put x is equal to 1 in given series. So what I get? 1 by 2 plus 1 by 3 plus 1 by 4 plus and so on, right? It is like summation n is equal to 2 to infinity 1 by n, which is divergent by P series. Case 2, put x is equal to minus 1 in given series. What I'll get? 1 by 2 minus 1 by 3 plus 1 by 4 and so on, which is an alternating series. It is convergent by Leibniz test. We know that we have done this converges with Leibniz test. Okay, so therefore interval of convergence is minus 1 less than or equal to x less than 1. This is the interval for convergence. Okay, minus 1 less than x less than was the interval of convergence, and here when we use x is equal to minus 1 also the series got convergent. So therefore I am adding here equal to sign. Okay, problem 2. Find the interval of convergence of the series 1 by 1 minus x plus 1 by 2 into 1 minus x whole square plus 1 by 3 into 1 minus x whole cube plus and so on. See that again we don't have the value of x, whether it is positive or negative, right? Given series is 1 by 1 minus x plus 1 by 2 into 1 minus x whole square plus 1 by 3 into 1 minus x whole cube plus and so on. Okay, so I can write here the nth term as 1 by n into 1 minus x whole power n plus and so on. So it is of the form summation n equal to 1 to infinity un, where un is equal to 1 by n into 1 minus x whole power n. So here I don't know whether x is positive or negative. What happens to that, right? So I cannot write directly that it is greater than 0. So I need to take modulus to that. So mod un is equal to 1 by n into 1 minus x whole power n greater than 0. It gives a positive series, right? So mod un by un plus 1 with limit n tends to infinity. I'm using again the D'Alembert ratio test, which is equal to limit n tends to infinity mod of, okay, un by un plus 1. So 1 by n into 1 minus x whole power n by 1 by n plus 1 into 1 minus x whole power n plus 1. Okay, so this is equal to limit n tends to infinity. I'll get that as 1 by n into modulus of 1 by x whole power n by 1 by n plus 1 into 1 minus x with mod whole power n plus 1. Then rewriting this, I'll get that as limit n tends to infinity mod un by un plus 1 is equal to limit n tends to infinity 1 by, okay, n into modulus of 1 minus x whole power n into, okay, I'll get that as n plus 1 into modulus of 1 minus x whole power n into modulus of 1 minus x whole power 1. So this is equal to limit n tends to infinity, okay, I'll get that as n plus 1 by n into, here after cancellation of these two, this and this, okay, what I'm having is, okay, mod of 1 minus x whole power 1. Then here I'll get the answer as limit n tends to infinity, okay, modulus of 1 plus 1 by n into mod of 1 minus x. So here I'll get the answer of mod of 1 minus x. So mod of 1 minus x greater than 1 converges, okay, and modulus of 1 minus x equal to 1 test fails. So what I'll have here is, okay, I can write this as minus 1 less than, so I can write it as 1 minus x greater than 1 or 1 minus x less than minus 1. Okay, so I can write this as 1 minus x greater than 1. So I'll get here minus x greater than 0 or I'll get x less than 0. And from this what I'll get here is, okay, minus x less than minus 2. It implies x is greater than 2, right? So I can write here x less than 0. I can write 0 greater than x greater than 2, right? 1 minus x greater than 1. It converges. We got this, okay, un plus 1. We got this, and after the cancellations, we are getting that as modulus of 1 minus x whole power 1. Okay, as so modulus of 1 minus x, if greater than 1, only it converges, right? So 1 minus x greater than 1 or 1 minus x less than minus 1. So it is giving the conditions as 0 greater than x greater than 2. So this is the interval of convergence, and here modulus of 1 minus x is equal to 1. It implies 1 minus x is equal to 1, 1 minus x is equal to minus 1. So it gives here x is equal to 0, and it gives here minus x is equal to minus 2 or x is equal to 2. If x is equal to 0, then we get 1 by 1 plus 1 by 2 plus 1 by 3 and so on. So diverges by p-series test. By p-series test it diverges. Okay, when x is equal to 2, what I'll get here? 1 by, okay, 1 minus 2 plus 1 by 2 into 1 minus 2 whole square plus 1 by 3 into 1 minus 3 whole 1 minus 2 whole square plus cube and so on. So it gives minus 1 by 1. Okay, plus here 1 minus 2 whole square. So I'll get minus 1 by 2. And here 1 minus 2 is 1. So cube, minus 1 cube is minus. So minus 1 by 3. Here minus 1 by 1 plus 1 by 2 minus 1 by 3 plus and so on, which converges by Leibniz test. Positive series, it diverges by P series test. Okay, here this is an alternating series, it converges by Leibniz test. So therefore, interval of convergence is, okay, so I can write here 0 greater than x greater than or equal to. With this, the unit, sequence and series is complete.